I'm in
Hi.
Nice, and
Mr.
yeah,
Derek.
so schools, university, everything is closed down today due to the storm.
The classical theorem by Bogomolov-Tian-Todorov, which I call the BTT theorem. So BTT theorem tells you that if you have a compact Kähler manifold X0 with trivial canonical bundle omega X0, that's what I denote the canonical bundle, then the deformations of X0 are unobstructed. So let me remind you what that means. So we have the so-called Koronischi family, that is a family of deformations of X naught, and I call X to def X naught this family, and it comes the Koronischi space. So def X naught is called the Koronischi space. It comes with a distinguished point, and the fiber over it is X naught. That's what the deformation is, and it is depending on whether you have infinitesimal automorphisms or not. This is either a miniversal or a universal even family, and then the unobstructedness of deformations is to say that, this space here is smooth. And as soon as you know it's smooth, you know that its dimension is given by the dimension of the first cohomology group of the tangent sheaf. And because you're numerically trivial, and let's for the moment assume that this variety is actually trivial, I can identify this with H1 of omega X naught to the n minus 1, which is a Hodge number, which is H n minus 1 comma n minus 1 comma 1 of your variety X naught. Okay, and that is an important theorem that tells you something about deformations of numerically k-trivial varieties, and that has been helpful in very many situations. So as we've already seen in this school, there is the recent interest to generalize theory from smooth varieties to singular varieties. So the question I would like to address is, what about singular varieties? So do we have a BTT theorem for singular varieties for the appropriate class of singularities? And there is a bad news in this direction, namely by Mark Gross, an example I think from the early 90s. So he gave an example of a Calabi-Yau n-fold. Calabi-Yau n-fold X naught with canonical singularities such that the space of deformations of X naught, the Koronischi space, has two components. So that's your X naught, and then there are two components, and obviously then this means that the space is singular. So there is a positive result, on the other hand, by Namikawa. Namikawa saying that symplectic varieties are, let me put it like this, certain singular symplectic varieties have a smooth def x naught. So maybe I should have said not certain, but many, because I mean it's really a large class of varieties that Namikawa's results apply to. And if you see this, then you could think that there is, some sort of dichotomy between Calabi-Yau and singular symplectic varieties. And well, that is of course the case if you look at arbitrary deformations, but in recent years, it has proven helpful to look at a certain subclass of deformations, which is much more suitable for Hodge theory. So-called locally trivial deformations. So let me turn to locally trivial deformations. Locally trivial deformations. And you remember that, for example, the tangent space to the Kuranishi space at the distinguished point 0 is given by an extension group of sheaves on X, namely it's the omega of X 0 into O of X 0. So that's the tangent space to the space of all deformations. And then if you look at the local to global spectral sequence for X, for example, then you get an inclusion of H1 of the tangent sheaf to this. And this inclusion is an equality for smooth varieties. So in general, the H1 of Tx naught, so in general means for singular varieties, the H1 of Tx naught is the tangent space to locally trivial deformations. Let me remind you what this is. So definition, I have X naught, a compact or complex variety. What's a locally trivial deformation of that? That's of course, well, first of all, that's a deformation X over S. The distinguished point, the fiber over this distinguished point is X naught. And then the following holds. So for every point in, say, X naught, you find an open U, which decomposes as a product, like U naught times S, and this commutes with the projection to S. So U naught is obviously U intersected with X naught. So that means that for every point in here, the central fiber of your deformation, you find a small neighborhood such that the deformation is actually a trivial deformation. So that's something that, as you know, holds for smooth varieties. And for singular varieties, that's a condition you impose. And that is a very useful condition because, well, first of all, it allows you to really make statements and examine the singularities that your space X naught has. It's also very well suited for Hodge theory. So for example, something that's known is if X to S is locally trivial, then in fact, in the smooth case, you have Ehresmann's theorem, and in the locally trivial case, you basically also have. So then X over S, at least up to shrinking S, is C infinity isomorphic to X naught cross S. so at least C infinity isomorphic to that. And this is due to Amerik Revitsky. So in particular, all cohomology that you're looking at in this deformation behaves as a local system. So the question would be, well, there is a subspace of the space of all deformations, which is the space of locally trivial deformations. So, that is the subspace of def of x naught, parametrizing locally trivial deformations. So is this smooth? So in other words, are locally trivial deformations unobstructed? And let me briefly tell you what is known in this direction. So known cases include Mark Gross. You know that Clavier threefolds have unobstructed locally trivial deformations. Then by joint work with Baker, if you have a singular symplectic variety, and this means compact log terminal singularities for GK class C. So in particular, you can talk about hot structures. I think that's all I need. Then you also have unobstructed locally trivial deformations. So if your variety is K-trivial, should say that's by result by Graf-Schwald. If your variety is K-trivial, or probably even only numerically K-trivial, and of class C, log terminal singularities. And then what they use as an additional assumption is either quotient or toric singularities. Then locally trivial deformations are also unobstructed. And there is some, work in progress. That's the part that I was referring to. That's it's work in progress. We have a method that up to now, reproduces the result of Graf-Schwald for quotient singularities and adds some minor cases, and we're trying to improve this method in order to be able to prove Bogomolov-Tian-Todorov theorem in a greater generality. But for today, the goal of my talk is something different, namely, suppose that BTT holds. What are applications? And again, in the work by Graf-Schwald that I already mentioned, they make the same assumption. So they assume that the space of locally trivial deformations to your variety is smooth. And then they show that strong algebraic approximation holds. That means that you can, so if your space def lt x naught looks like this, here is your central point, then you can arbitrarily close to this point find points such that the corresponding fiber, so t say such that xt is projective. So you can, in the local moduli space, you can approximate your variety, which is Kähler. Yeah, sorry, this I should add. You must have a Kähler assumption, obviously. You can approximate it by varieties which are projective. Okay, and here I should really say now, from now on, if I speak about BTT, that means a locally trivial BTT. Okay, and the result that I'm going to speak about today is the decomposition theorem. So in other words, if we assume that there is a locally trivial BTT, then we're able to prove a decomposition theorem, as it has already been on the board, or on the slides, I should say, in this school. So let me just recall it by Bogomolov-Beauville. So let X be a say compact Kähler manifold with omega x numerically trivial then there is a finite topological cover x prime to x such that the following holds. Well, this x prime, as you know, decomposes as a product in a torus, some Calabi-Yau factors, and some factors by irreducible symplectic varieties. So this is a torus. These are Calabi-Yau. And these are irreducible symplectic. We won't need the precise definitions of Calabi-Yau and irreducible symplectic, and I think they have also already been mentioned. What I would like to tell you next is that, as you have already heard, there is a singular version of this theorem in alphabetic order. People who contribute are at least, I hope I don't forget too many people, so Druel, Grep, Genancia, Höring, Kivicus, Petonel, and I hope that that's the order of the alphabet. Okay, I should say that the final result has been proved by Höring and Petonel in 2017, but it's, I think as far as I understand, the result of a lot of efforts of several people, most of which I hopefully I now named. And so what's their statement? So you have to change a compact Kähler manifold into, well, you allow singularities. So you can say a variety with log terminal singularities. Therefore, you need to look at projective varieties. Omega is numerically trivial, and then the statement slightly changes. So from a finite topological cover, you go to a finite quasi-étale cover, which in the smooth case is just the same thing. But then some of the obvious question is, so you have this result for singular projective and for smooth Kähler varieties. Now, in this school, singular Kähler varieties already have been discussed. So the question is, what about singular Kähler varieties? And that's the result I want to announce. So let me put it like this. So if a locally trivial BTT holds, then the Bogomolov, Bovil, Duruel, Greb, Genancia, Höring, Kevikos-Petanel theorem decomposition holds for singular, so for log terminal Kähler, compact Kähler varieties with numerically trivial canonical bundle. Okay. So let me tell you at least what goes into the proof. So the main idea of the proof is that you reduce to the projective case. Use to the projective case using the BTT plus algebraic approximation. So this uses the Graf-Schwald result, and then obviously you use the decomposition theorem. In the projective case, by what I just announced, and then of course once you have the decomposition, so you have a deformation by BTT, and then say on neighboring fibers you find an algebraic variety by Graf-Schwald, by algebraic approximation. Then you decompose. I mean, of course, first you go up to a finite étale cover, you decompose, and then you want to go back. And that's the main task. Let us try to show how to go back. And this uses arguments using cycle spaces. And another important ingredient is the relative version of the GKP foliation. Right? I mean, you remember that before you decompose the variety, first of all, you decompose the tangent bundle or the tangent sheaf. And what I'm telling you is that if you have a locally trivial deformation, then you can do that in families. So you use a relative version of this foliation, and then you use singular Kähler-Einstein matrix, as we've already seen in this school by Isidieu, Getsch, and Seriai, and the Kähler case by a result by Paul. And that's the basic strategy. Now, in the time that I've left, I would like to elaborate on that. Okay. So the first step is the following, something I could call Zariski openness of the decomposition locus and the precise statement is this. So if you have X to S, a locally trivial family, and I'll assume actually that this is a family over the locally trivial Kuronishi space of X naught. So it's a locally trivial family. So X naught numerically K trivial. Class C, log terminal singularities, and you have point S in S, such that, yeah, I think I could say, so X S, meaning the fiber over the point S, decomposes as X1 of S times up to, say, M of S. So we have a product decomposition, which of course is then a sort of non-empty condition once you invoke the algebraic approximation and the projective decomposition theorem. So now I assume in addition that H1 of OXI comma S is equal to 0, and the same holds true for H naught of TXI comma S whenever I is different from 1. So in other words, for all but one factors of this decomposition, well, essentially what I want is that they're not the torus, right? I mean, you remember that in this decomposition there is a torus showing up, and I want the torus to be, or every torus part to be in X1 of S. So all of these are non-tori, and then the statement is there exists a S prime to S, which is finite, on S prime mapping to S, and U prime in S prime is Zariski open, such that the decomposition that you had at the point S, now after pullback to S prime, exists in families. So in other words, there exist, how to say, I think, yeah, let me phrase it like this. So the pullback, so X prime, which is X over S prime with S, is isomorphic. So once you're restricted to U prime, yeah, once you're restricted to U prime, you can say it's isomorphic to say x1 prime product over u with x2 prime product over u, oops, until xm prime, where x, xi prime over u prime, u is u prime, deformations, so locally trivial deformations of xis. Okay, I should say s primes inside here. That's a bit lengthy. Let me recall what I just tried to say. So so it's the Zariski openness of the decomposition locus. We start with a locally trivial deformation, which I assume to be the miniversal locally trivial deformation. And I suppose that I have one point such that the fiber in this point decomposes as a product. Well, if xs is k-trivial, then also all of these guys have to be k-trivial. And the only condition I have is that there's no sort of like flat contribution in these factors. Oh, I should better say, sorry, I should be more precise. I should say there's no torus-like contribution in these factors, meaning they all have vanishing H1O and vanishing H0T. And there is a finite cover such that the pullback to this finite cover decomposes as a product. So from one point, you go to a Zariski open set where your decomposition theorem holds. Then, of course, the important task is to sort of take the limit, right? So let me still try to give an idea of the proof of step one. So the essential thing that you use is that that the tangent sheaf decomposes, right? So Txs decomposes as Tx1s, box sum with Tx2s, and so on, Txms. And this, of course, induces a decomposition of, say, H1 of Txs is given as a direct sum I from 1 to m of the H1s of Txis. And then you use the locally trivial BTT. So I should mention here in this implication, that's the point where the assumption on the vanishing of the cohomology groups goes in. So then you use the BTT. So BTT gives you families. So X, let me put it like this. So there is a family X1 over def of X1s. And there is xm over def of def lt, I should say, def lt of xms. And then, of course, you have the family x1 product until xm over the products of the deformations of the Koronischi spaces xi, si from 1 to m, right? And that's sort of the problem is that so this thing here that only gives you a Euclidean open in S, so the base of the deformation that I started with. And you want to extend this Euclidean open to a Zariski open. But on S, you fail because there could be for example, monodromy effects. Yeah? I mean, you have a decomposition, say, in two factors, x1, x2. You start with x1, you go around in a loop, and you come back as x2. So in any case, the remedy here is that you use the cycle spaces argument in order to give you S prime to S, such that you have this decomposition everywhere. Okay. Right. Good. So this was the first step. The second step, as I already indicated, is to use the decomposition theorem in the projective case plus algebraic approximation plus the first step. You reduce to the situation where you have x to f over some disk. You have x star over the punctured disk. Over the punctured disk, and say x star decomposes as x1 star times over delta star with x2 star. Now let's suppose that we just have two factors, and then the goal is, so this was step 2, this was this reduction, and now our goal is to produce families x1 over the disk and x2 over the disk, such that, well, to prolong these families x1 and x2 star, right? So in other words, xi restricted over the punctured disk is xi star, and x is isomorphic to the fiber product. So x1 over delta with x2 as spaces over the disk, right? And the idea is to use cycle spaces, or if you prefer duad spaces. So I let say d1 inside the relative duad space of x over s be the component containing all subspaces of the following form. So recall that, I mean, outside 0 we have a product, so I can take, say, x1t times you know, some fixed point p on x2t, and similarly for x2. Right. Okay. So now what you do is third step. So now you have to analyze the degenerations, right? I mean, you have this decomposition outside 0, so you have these cycles. And then, of course, what your idea is that if, you know, t tends to 0, then these cycles tend to some well-behaved, you know, x1 0 times some point p. And, you know, that's of course the great challenge, because usually there is really not much you can say for what the limit cycle of a degeneration would look like. So the important step is this one. So suppose you have this one parameter family, xt, t in delta, a family of subspaces in D1. So this I mean that, you know, generically for t different from 0, they look like, as I said, x1t times a point in x2t. Now I let them degenerate. And I wonder what kind of space I would get. And the statement is, so then y naught is irreducible and reduced. Okay, and that is a very strong statement, and the reason why one is able to prove such a statement. So philosophically, that's because you have locally trivial deformations, and there's not much degeneration happening in locally trivial deformations. But so this was philosophically, but then technically, you need, or at least the way we proceed is via singular killer Einstein theory. So that's pretty important here. So for the proof, so as I said, there is local triviality of deformations. And local triviality of deformations gives you that you have a Kuhnert decomposition. On x naught, right? So you know that the neighboring fibers decompose. You do not know that x0 decomposes, but by the result of American-Verbitsky that I mentioned before, well, C infinity wise, x0 decomposes, and therefore in particular, its cohomology decomposes. So we know decomposition on the level of cohomology and homology. So H2m of x naught is given by H2m of xt, and this can be decomposed as follows. So there is the factor H2m of x1 t plus H2m minus 1 of x1t tensor H1 of x2t, and so on. And you can also give a generator. So say if m is the dimension of the cycles that so here dimension of yt is equal to m, then here a generator is given by yt, and let me call tau this generator. So that's a generator of the first summand here in this Kuhnert decomposition. and now what I do is I suppose that y naught decomposes as, say, a plus b, right? So I want to show it's irreducible and reduced. I assume this is not the case. I decompose it as something of the form a plus b. And I write the class of A, I can write that as n times tau plus epsilon, where epsilon is contained, in these other factors. And if this is A, then the class of B has to be 1 minus n times tau minus epsilon. Then I do a computation. So let me put it like this. So I choose a Kähler form omega t on xt, and I decompose it omega t as omega t1 plus omega t2, where the omega ti are Kähler forms in the, on the factors x1t and x2t. So I'll comment in the end of it on why this is possible, or to be more precise, why this is actually not possible, but why what I do is still justified. Okay, so then you have to show that also omega 0 decomposes as some omega 0,1 plus omega 0,2. We don't know what they are. Well, the omega I0, that's sort of the limit in a certain sense of the omega IT. But we can't say that they come from product decomposition, because that's what we want to show, of course, right? And now, by a limit argument, you see that omega 0,2 restricted to y0 is equal to 0, right? Because that's true for like all the neighboring fibers. So omega 2t is 0 when restricted to yt. And then, because we sort of deal with forms now, this is something that propagates to the limit. And now you can argue as follows. So you know that following quantity is positive. So you have omega 0 to the m times y0. Recall that the class of this is given by tau. And now I use what I just said. Also here I should probably say this m is not 1 or 2, but it's the wedge product that I do. That is the same as if I do the mth wedge product, but now with the part omega 1, because I just explained that the omega 2 part is 0 when restricted to y0, right? And now I decompose as I did before. So on the one hand, this is a times omega 0, 1 to the m plus b times omega 0, 1 to the m. And both of these factors are strictly positive, right? Because the restriction of the Kähler form is nothing else as this first summand omega 0, 1. So what you intersect here is actually the component A, respectively B, with the top power of the Kähler form. So both of these summands are positive. But on the other hand, you know that, well, by the König decomposition, the first thing is n times tau times omega 0 to the m. And the second is 1 minus n times tau times omega 0 to the m. So that's, of course, not possible unless n is equal to 1, and therefore, say b is equal to 0. So this shows that there is the limit cycle is irreducible and reduced. And I want to stress that this is really a very strong statement about the degeneration of cycles, about which usually you know very little. And then you have a similar argument that shows you step 4. So step 4 is, well, now we had a statement about limits of cycles in one of the two families. We have two families of cycles coming from the two factors of the product decomposition. Right, so now I start with two families of cycles. So degenerating into 0, say ZT, T in delta, in the other component of the duality space. And then what happens? Well, on a generic fiber, you have the y's, or deformations of say yt, which are say fibers of the projection in one direction, and the zt are fibers of projection in the other direction. Well, as you have a product decomposition, obviously both cycles intersect in a single point. And something similar is true here, namely we have that at least we can show that the dimension of y0 cap z0 is 0. And the number of intersection points of y0 and z0 is equal to 1 on the regular part. So on the regular part, is everything is fine. Well, I should say for cycles which intersect at all in the regular locus, right? So I should say smaller or equal to 1. And the proof uses techniques that are similar to step 3. So it's Kähler-Einstein techniques and of intersection theory. And now the final step is the following. Final step is the following. So you look at these families D1 and D2, and then I look at I look at J, which is what I call the universal intersection. What I mean by universal intersection, well, first of all, I want to restrict over the central fiber. And by universal intersection, I mean a point inside there is given by, a cycle in D1, 0, a cycle in D2, 0, and a point of the intersection. Well, and then I pass to irreducible components. So I take I take an irreducible component here. Irreducible component here is such that the map that I have to x0 is dominant. And then what you show, so by the preceding steps, is that this map here is generically finite. No, sorry, it's actually finite by step 4, and also by step 4 is generically 1-to-1. And this map here is birational. And then you're close to done, because now just look at this. So if this is, if this is a finite morphism, generically 1-to-1, then you see that this space and this space have the same normalization. So the normalization here has a product structure. So it's D1 0 normalized times D2 0 normalized, mapping to here, then of course also mapping to here. And now you have a birational map from a product into a variety, and this is this is enough, as the following general lemma shows. So if you have if you have y times z, and the bimeromorphic map to x naught, and you have, say, h1 of O of z equal to 0. And so at least one of the factors, so in our language from before, one of the factors has a trivial Albanese. And this can only be the case if actually x naught is a product. So if you're bimeromorphically dominated by a product, then you are a product yourself. And you know, with this lemma, the decomposition theorem follows. And that's basically what I wanted to show you. So let me, I promised it, say a word about this bit of cheating that I do new here. So I said I pick a Kähler form, I decompose it, and then I look at the limits of this decomposition. So there's a bunch of remarks one should make. Namely, first thing is that, of course, once I have a once I have a Kähler form, I can look at its class, its Kähler class, and by Kunnert it will decompose. But a priori it's not clear, at least not to me, that also the form decomposes. And this is something that you achieve by basically the uniqueness result in the existence of Kähler-Einstein metrics. So you drop the condition of having a Kähler form, but you go to this singular Kähler forms that you have by Esselier-Gebschen seriae. And then somehow by the uniqueness of this form, you show that it decomposes. And then, of course, I mean, showing the existence of this limit, especially for like the two components, that's a non-trivial statement. And it uses, so what does it use? Basically, it uses on the regular part, it uses the relative foliation that I was speaking of before. So if you have this relative foliation, I mean, recall this foliation is something that that is supposed to be the relative tangent space of the factors. And once, you know, once your tangent sheaf decomposes, at least on the regular part, also forms decompose. And therefore you have this decomposition on the regular part. And then an important ingredient is that you have to show that its integral does not explode if you approach the singular locus. And for this you use the local triviality of the deformation. So there is a lot of Kähler-Einstein that I have hidden. And so what I learned from working on this question is that some more Kähler-Einstein theory allows you to argue as, so to say, as in the smooth case, but you know, with a lot of technicalities, of course, that have to be verified, but it's very useful. And yeah, this was all I was going to say. So thank you very much for the attention. And as I'm the last speaker of this meeting, let me also take the opportunity to thank the organizers for putting these meeting and these lecture series together in these extraordinary times, which is a very good initiative. So I'm very grateful to everybody for listening, and especially to Dima and Nikon for organizing. Thanks.
Thank you.
Thank you, Christian. Yeah. Yeah.
As for me, it's Nikon actually. Yeah.
Okay. Thank you. Any questions to Christian?
Yeah, that's very clear talk, but very complicated. I mean, lots of. But Christian, this is published, is it? I mean, like a preprint or something?
Not yet.
Okay, but it's gonna be soon, probably.
Not yet. I mean,
It's
there are
partially
these
published,
parts.
right? The first part is published, right?
Okay.
No, actually not. I mean, some of the results that I mentioned are published when I was speaking about known results. So, for example, these results about the symplectic varieties, they are published in a joint article with Ben.
No.
But somehow, so here we have these two parts. The second one is application of BTT to the decomposition theorem, which is fairly complete. But of course, we're trying to get some more cases where the BTT actually holds. So that is sort of why it's not yet on the archive.
And so, I mean, you use cycles, right, for degeneration. A priori, you could think you could try to generate, I don't know, foliations or something else, and blah 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 blah. But somehow, it's the cycles that work in the end, right?
Yes, some of the reason is that, well, we have this relative decomposition of the foliation, but, and I think that's also already the case in the projective situation. If you have the foliation, then of course you have something like local integrability at smooth points. But at singular points, it's not so clear to me what the existence of such a foliation actually tells you. So and that's also more or less what happens here in our situation. It's pretty easy to control everything on the smooth locus, but what happens on the singular locus is not so clear. And well, we tried with the foliation, but as I said already in the projective case, I think it's quite difficult even from the foliation to come to a global integrability result. So, yeah, right.
And is it important to use Duodie, or you could use Barlet, or?
Actually, it's we use Duodie, but we could also use Barlet actually, because you see in this step 3 and 4 that I mentioned, so the how to say, the irreducibility and reducedness, also the dimension of the intersection. Well, the second statement is maybe a little stronger if you state it in terms of Duodie than in terms of Barlet, but I think there's not a big difference. So I think step 3 and step 4 are more or less equally difficult for Barlet or Duodie spaces.
Okay. Okay. Thank you.
Okay, thanks.
More questions? Let's start. Okay, let's thank Christian again.
Thank you very much for the invitation.
Thank you.
And thanks all of you